Welcome to this coding walkthrough. In this session, we'll dive into solving LeetCode problem number 219, contains duplicate 2. This problem is a great opportunity to explore efficient ways of detecting duplicates within specific constraints. Let's get started. The problem asks us to determine whether there are two distinct indices in the given array where the values at those indices are equal, and the distance between those indices is no greater than a given value, k. Specifically, this means we need to check two conditions: first, that the values at the indices I and j are the same, and second, that the absolute difference between the indices I and j is less than or equal to k. If both conditions are satisfied, we return true, otherwise, we return false. The input consists of an integer array nums and a non-negative integer k. The output is a Boolean value, true if the conditions are met, and false otherwise. To illustrate, let's consider an example where nums is 1, 2, 3, 1, and k is 3. In this example, the output is true. The reason is that the value 1 appears twice in the array, specifically at indices 0 and 3. The absolute difference between these indices is abs, 3 to 0, which equals 3. Since this difference is less than or equal to k, the function returns true. Another example uses the input nums equals 1, 0, 1, 1, and k equals 1. Here, the output is also true because the value 1 is found at indices 2 and 3. The absolute difference between these indices is abs, 3 to 2, which equals 1, and this satisfies the condition of being less than or equal to k. Next, consider an example where nums equals 1, 2, 3, 1, 2, 3, and k equals 2. In this case, the output is false. While the array does contain duplicate values, none of them satisfy the required condition. For instance, the closest occurrences of the value 1 are at indices 0 and 3, but the absolute difference abs, 3 to 0, equals 3, which is greater than k equals 2. Similarly, for the values 2 and 3, no pairs of indices meet the condition. As a result, the function returns false. Finally, let's consider the constraints. The length of the array can range from 1 to 100,000, and the values in the array can range from -1 billion to +1 billion. Additionally, the value of k can range from 0 to 100,000. Now, let's discuss some edge cases. First, if the array contains only one element, such as nums equals 1 and k equals 0, no duplicates exist, so the output will always be false. Second, for very large arrays, such as when nums contains 100,000 elements and k is also large, the solution must be efficient and operate within O(n) time complexity to avoid performance issues. Third, the array may contain negative values, but this does not affect the logic since equality and absolute difference calculations work the same way regardless of negativity. Lastly, if k is 0, it is impossible for any two distinct indices to satisfy abs, ij equals k, so the result will always be false in such cases. To begin solving this problem, we can first consider the brute force approach. This method is straightforward. We compare every possible pair of indices in the array and check two conditions. First, whether the elements at those indices are equal, and second, whether the difference between their indices is less than or equal to the given value k. To implement this, we use two nested loops. The outer loop iterates over each element in the array, while the inner loop checks the next k elements to see if any of them satisfies both conditions. If we find such a pair, we return true immediately. However, if no such pair is found after examining all possibilities, we return false. While this approach is simple, it has a time complexity of O(n*k), making it inefficient for large arrays or cases where k is close to n. Additionally, it uses constant space since no additional data structures are involved. The brute force approach, while easy to understand, struggles with efficiency for larger inputs. To address this, we can use an optimized approach with a hash map. The intuition here is that instead of checking every pair of indices, we can keep track of the most recent index of each number using a hash map. By doing this, we can quickly check if a number has reappeared within the desired range. Specifically, as we iterate through the array, we check if the current number already exists in the hash map, and if the distance between the current index and the stored index is less than or equal to k. If both conditions are met, we return true. Otherwise, we update the hash map to store the current index of the number. This approach is much faster, with a time complexity of O(n), since we only traverse the array once. However, it does require O(n) space to store the indices in the hash map. The hash map approach is efficient, but it does require additional memory. Another alternative is the sliding window technique using a hash set. Instead of tracking indices, we maintain a hash set to represent a sliding window of size k, containing the unique elements within that range. As we iterate through the array, we ensure the hash set only contains the most recent k elements by removing the oldest element if the size exceeds k. If the current number exists in the hash set, it indicates a duplicate within the window, and we return true. Otherwise, we add the current number to the hash set. This approach also has a time complexity of O(n), as we process each element once, but it reduces space usage to O(k), which can be advantageous when k is much smaller than n. While both the hash map and sliding window approaches are efficient, they come with their own trade-offs. The hash map method is straightforward and easy to implement, as it directly tracks the indices and avoids manually managing a sliding window. This makes it a good choice for most scenarios. However, it does require O(n) space, which might not be ideal for memory-constrained environments. On the other hand, the sliding window approach uses less memory, requiring only O(k) space, but it involves slightly more complexity in maintaining the window. Ultimately, the choice between these strategies depends on the specific constraints of the problem, such as the size of k relative to n and the available memory. Overall, the hash map approach strikes the best balance between simplicity and efficiency. It efficiently handles the problem in O(n) time and is relatively easy to implement and debug, making it the preferred solution for most cases. The key insight is that by directly tracking the most recent index of each number, we can quickly calculate the distance between indices without the need for extra overhead. While the sliding window approach offers a memory-efficient alternative for scenarios where k is significantly smaller than n, the hash map method generally provides a more straightforward and robust solution to this problem. To solve this problem, we start with the brute force approach, which is the simplest way to think about it. The idea is to check all possible pairs of indices in the array and verify if they meet the two conditions. First, the elements at these indices must be equal, and second, the absolute difference between the indices must be less than or equal to the given value of k. To implement this, we use a nested loop. The outer loop fixes the first index I, starting from 0 and going up to the second to last element. The inner loop picks the second index j, starting from I plus 1, ensuring that the indices are distinct. For each pair, I, j, we first check if the elements nums, I, and nums, j, are equal. If they are, we then calculate the absolute difference ij, and verify if it meets the condition ij equals k. This approach systematically examines all possible pairs but can become computationally expensive for larger arrays. Once all pairs of indices have been evaluated, we can determine the result. If any pair satisfies both conditions, we immediately return true, as we've found a valid pair. However, if we finish checking all pairs and no such pair exists, we return false. Now, while this brute force approach is straightforward, it's inefficient for large arrays due to its nested loops. To optimize this, we can use a different approach that combines a sliding window technique with a hash map. The intuition here is to avoid redundant comparisons by focusing only on numbers within a certain range of indices and using a hash map to track the most recent index of each number. We start by initializing an empty hash map, number_map, which will store the most recent index of each number in the array. Then, as we iterate through the array, we check whether the current number already exists in the hash map. If it does, we retrieve the stored index and calculate the distance between the current index and the stored index. If the distance is less than or equal to k, we return true immediately. After evaluating a number, regardless of whether a match was found, we update the hash map to record the number's current index. This ensures that the hash map always holds the most recent index for each number, which is crucial for maintaining efficiency. If we complete the loop without finding a valid pair, we return false. This optimized approach addresses the limitations of the brute force method. While the brute force approach has a time complexity of O(n², making it impractical for larger arrays, the sliding window approach significantly reduces unnecessary comparisons. By focusing only on indices within the range defined by k and leveraging the hash map for constant time lookups, we achieve a time complexity of O(n), Additionally, the hash map stores only the most recent indices, ensuring that space usage scales linearly with the number of unique elements in the array. The hash map plays a critical role in this algorithm. It allows us to efficiently track the most recent occurrence of each number, ensuring that lookups and updates happen in constant time. This efficiency is what makes the optimized approach scalable, even for large arrays. There are also a few edge cases to consider. For instance, when k is 0, no valid pairs can exist, as the indices must be distinct and the distance between them would always be greater than 0. Additionally, if there are duplicate numbers in the array but their indices are farther apart than k, they should not be counted. Arrays that are empty or contain only a single element also return false since no pairs can exist. The key data structure here is the hash map, which holds the most recent index of each element, and it allows us to maintain the sliding window efficiently. Overall, the algorithm achieves an O(n) time complexity from a single pass through the array and O(n) space complexity from storing up to n unique elements in the hash map. Let's walk through an example to solidify our understanding of the optimized approach. Suppose the input is nums equals 1, 2, 3, 1, and k equals 3. We start by initializing an empty hash map, number_map equals. At index I equals 0, the value is 1, which is not in the hash map, so we add it, number_map equals 1 o'clock. Moving to index I equals 1, the value is 2, which is also not in the hash map, so we add it, number_map equals 1 o'clock, 2, 1. At index I equals 2, the value is 3, which is not in the hash map, so we add it, number_map equals 1 o'clock, 2, 1, 3, 2. Finally, at index I equals 3, the value is 1, which does exist in the hash map at index 0. We calculate the distance of 3, 0 equals 3. Since this is less than or equal to k, we return true. For another case, if nums equals 1, 2, 3, 4, and k equals 1, there are no duplicate values, so the hash map is updated throughout, but no valid pair is found, and we return false. This solution for LeetCode problem number 219 contains duplicate 2, utilizes a dictionary to efficiently track the indices of elements in the input list nums. The goal is to identify whether there exist two indices I and j such that the values at these indices are equal, nums I equals nums j, and the absolute difference between the indices I j does not exceed k. The function contains nearby duplicate begins by initializing an empty dictionary number_indices to store the most recent index of each number as it is encountered during iteration. The iteration over the array nums is performed using a for loop with enumerate, which provides both the index, I, and the value, number, of each element. Inside the loop, the code first checks if the current number is already present in the dictionary number_indices. If it is, the function calculates the difference between the current index I and the previously stored index of number. If this difference is less than or equal to k, the function immediately returns true, indicating that the conditions are satisfied. If number is not found in the dictionary or the index difference exceeds k, the function updates the dictionary by setting the current index I as the last seen index for number. This ensures that the dictionary always holds the most recent index for each number. If the loop completes without finding any such pair of indices, the function returns false. The algorithm has a time complexity of O(n), where n is the length of the input list, as it traverses the list once and performs constant time operations for dictionary lookups and updates. The space complexity is O(n) k, as the dictionary stores at most k entries at any time due to the problem's constraints. This is the Java implementation of LeetCode problem number 219, contains duplicate 2. The logic mirrors the provided Python solution, using a hash map to store the last seen indices of elements in the array. Key differences include explicit type declarations for the hash map and variables, as well as the usage of Java's map interface and put method. The method iterates through the array, checking if a duplicate exists within the given range k. If found, it returns true, otherwise, it returns false after the loop completes. To solve this problem, we start by initializing an empty dictionary called number_indices. This dictionary will help us track the last seen index of each number in the array. In the first iteration, the number is 1 at index 0. Since 1 is not in the dictionary, we add it with its index. Now, number_indices becomes 1 o'clock. In the second iteration, the number is 2 at index 1. Again, 2 is not in the dictionary, so we add it with its index, updating number underscore indices to 1 o'clock, 2, 1. Next, in the third iteration, the number is 3 at index 2. Since 3 is also not in the dictionary, we add it, and now number underscore indices becomes 1 o'clock, 2, 1, 3, 2. Finally, in the fourth iteration, the number is 1 at index 3. This time, 1 is already in the dictionary, and we calculate the difference between the current index and the last seen index, which is 3, 0 equals 3. Since this difference is less than or equal to k, which is also 3, the condition is met, so we return true as the result. In this example, the array is 1, 0, 1, 1, and k is 1. Again, we start by initializing an empty dictionary number underscore indices. On the first iteration, the number is 1 at index 0. Since 1 is not in the dictionary, we add it with its index, resulting in number underscore indices equals 1 o'clock. On the second iteration, the number is 0 at index 1. Since 0 is not in the dictionary, we add it, updating number underscore indices to 1 o'clock, 0, 1. On the third iteration, the number is 1 at index 2. Now, 1 is already in the dictionary, but the difference between the current index and the last seen index is 2, 0 equals 2, which is greater than k. Because the condition is not satisfied, we update the last seen index of 1 to 2, resulting in number underscore indices equals 1, 2, 0, 1. On the fourth iteration, the number is 1 at index 3. This time, 1 is in the dictionary, and the difference between indices is 3, 2 equals 1, which is equal to k. This satisfies the condition, so we return true as the result. Here, the array is 1, 2, 3, 4, 5, and k is 2. We begin with an empty dictionary number underscore indices. On the first iteration, the number is 1 at index 0. Since 1 is not in the dictionary, we add it, resulting in number underscore indices equals 1 o'clock. On the second iteration, the number is 2 at index 1. As 2 is not in the dictionary, we add it, updating number underscore indices to 1 o'clock, 2, 1. On the third iteration, the number is 3 at index 2. Since 3 is not in the dictionary, we add it, resulting in number underscore indices equals 1 o'clock, 2, 1, 3, 2. On the fourth iteration, the number is 4 at index 3. Since 4 is not in the dictionary, we add it, updating number underscore indices to 1 o'clock, 2, 1, 3, 2, 4, 3. On the fifth iteration, the number is 5 at index 4. As 5 is not in the dictionary, we add it, resulting in number underscore indices equals 1 o'clock, 2, 1, 3, 2, 4, 3, 5, 4. By the end of the loop, no duplicates are found within a distance of k, so we return false as the result. To summarize, the algorithm uses a dictionary to store the last seen index of each number in the array. For every number, it checks if the number exists in the dictionary and calculates the difference between the current index and the last seen index. If this difference is less than or equal to k, the condition is satisfied, and the algorithm returns true. If not, it updates the dictionary with the current index and continues processing the next number. The algorithm operates with a time complexity of O(n), as we only iterate through the array once, and a space complexity of O(n), due to the storage of indices in the dictionary. For the provided examples, the outputs are true for the first example, true for the second, and false for the third. In this algorithm, the time complexity is O(n), where n represents the length of the input list nums. Let's break this down step by step. First, the loop iterates over the list using the enumerate function, which processes each element exactly once. This contributes an O(n) factor to the time complexity. Next, we have dictionary operations, such as checking if a number is already in the dictionary and updating it with the current index. These operations, thanks to Python's efficient hash table implementation, are performed in constant time, or O(1), on average. Since these dictionary operations occur once per iteration, their total contribution across the entire loop is another O(n). By adding these contributions together, we get O(n) plus O(n) equals O(n) as the overall time complexity. Now, let's analyze the space complexity, which depends on the size of the dictionary number underscore indices used to store elements and their indices. the dictionary stores at most min, n, k plus 1 key value pairs at any given time. This is because the algorithm only tracks numbers within a sliding window of size k. If the window moves forward, older entries are effectively replaced by newer ones. In the worst-case scenario, if k is larger than the size of the list n, the dictionary will contain all n elements, leading to a space complexity of O, n. However, if k is smaller than n, the dictionary size is limited to O, k. Therefore, the overall space complexity is O, min, n, k, as it reflects the smaller of the two values. Let's consider the best, average, and worst-case scenarios for this algorithm. In the best-case scenario, the algorithm finds a nearby duplicate early and terminates quickly. For instance, if the duplicate is found in the second iteration, the loop would only require O1 iterations, resulting in a best-case time complexity of O1. However, the space complexity remains O, min, n, k, as it depends only on the size of the sliding window. In the average case, the algorithm typically processes a majority of the list before finding a duplicate or returning false, resulting in a time complexity of O, n. The space complexity is still O, min, n, k, as the dictionary size is constrained by the sliding window. Finally, in the worst-case scenario, no duplicates are found within the given distance k, so the algorithm processes all n elements, leading to a time complexity of O, n. The space complexity in this case also remains O, min, n, k. To compare approaches, consider the brute force method. This naive solution uses nested loops to check the distance between every pair of duplicate numbers. For each element, it iterates over the next k elements to find duplicates, resulting in a time complexity of O, n asterisk k, asterisk asterisk. While its space complexity is minimal at O1, due to the lack of additional data structures, this approach is highly inefficient for large inputs. In contrast, the optimized solution, our current algorithm, uses a dictionary to store indices and restricts checks to a sliding window of size k. This reduces the time complexity to O, n, a significant improvement. While the space complexity increases slightly to O, min, n, k, this trade-off is acceptable given the major runtime performance gains. Finally, let's formally prove the big O complexity of this algorithm. For time complexity, the loop executes exactly n iterations, and each iteration involves constant time operations, such as dictionary lookups and updates. This results in a total of n asterisk O1 equals O, n, asterisk asterisk operations. For space complexity, the dictionary used to track indices stores a maximum of min, n, k, elements. This is because the algorithm only keeps track of numbers within a sliding window of size k, discarding older entries as the window moves forward. Therefore, the space complexity is O, min, n, k. With this, we have mathematically demonstrated that the algorithm runs in O, n, time and uses O, min, n, k, space. When tackling this problem, there are a few common mistakes to watch out for. First, overlooking edge cases can lead to issues. Examples include arrays with very few elements, such as size 1 or 2, or when the value of k is 0. These scenarios may result in unnecessary comparisons or incorrect results if boundary conditions aren't handled properly. Next, implementing a sliding window incorrectly can create problems. For instance, if you don't manage the window size appropriately while iterating through the array, like forgetting to shrink the window when needed, you can either miss valid pairs or waste computation time, which impacts efficiency. Another frequent mistake is relying on a nested loop, brute force approach. While straightforward, this method has a time complexity of O, n squared, and becomes impractical for larger inputs, such as arrays with up to 10 to the power of 5 elements. Optimized solutions like hash maps or sliding windows are much better suited for such cases. Another pitfall is misinterpreting the problem constraints. For example, some may confuse the condition I j equals k with nums I nums j equals k. This misunderstanding leads to incorrect logic and invalid outputs. Likewise, not managing duplicate keys properly in hash maps can cause issues. If you overwrite indices or fail to track duplicates accurately, you risk missing valid results. Now, let's talk about some key takeaways for interviews. Recognizing patterns, such as the sliding window technique or leveraging hash maps, is crucial for problems like this. Trade-offs also matter. A brute force solution might work for small inputs but is unsuitable for larger constraints, so optimizing for time and space complexity is essential. Lastly, when explaining your approach, always articulate your reasoning clearly. Discuss why you chose a specific method, highlight its trade-offs, and demonstrate your understanding of the problem. This problem is closely related to several others on LeetCode. For example, LeetCode 217 contains duplicate, shares a similar focus on identifying duplicates. LeetCode 438, find all anagrams in a string, and LeetCode 3, longest substring without repeating characters, also involve sliding window techniques or hash maps for efficient solutions. Of course, LeetCode 219 itself is directly related as a variation. Now, let's consider alternative approaches to solving the problem. The sliding window combined with a hash map is an efficient method with a time complexity of O, n, and a space complexity of O, k. It works well for large values of k, but its memory usage depends on the window size. On the other hand, the brute force approach, with O, n squared, time complexity and O, 1, space complexity, is easy to implement but impractical for larger datasets due to its inefficiency. Another alternative is the bucket sort approach, which is a more advanced optimization. It has a time complexity of O, n, and a space complexity of O, k. This method is particularly effective at handling edge cases, but it requires a solid understanding of how bucket indexing works. While it's not as intuitive as the sliding window or hash map approach, it can be a powerful tool in your arsenal for solving this type of problem efficiently. Ultimately, the choice of approach depends on the specific constraints of the input and the trade-offs you're willing to make between time and space complexity. Great job making it to the end. To summarize, we tackled problem number 219 by exploring brute force and hash map-based solutions, emphasizing efficiency and best practices. Remember to keep practicing similar problems to solidify your understanding. Thanks for watching, and I'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!